Okay, this is my last video for calculating delta G, or the thermodynamic favorability of a reaction. And it has to do with things at equilibrium. Okay, so this is for reversible processes, specifically reversible chemical processes. And so we, of course, have to bring in the equilibrium constant K. So here's the equation for free energy with regards to equilibrium. All right, it is delta G, okay, equals delta G naught. And that's right, remember, 25 degrees Celsius and 1 atmosphere, which we can calculate if we look them up online, plus R, that's the gas constant, T, L, N, Q. All right, we actually know what all these values are. R is the gas constant. Okay, now we are talking about energy, and these are going to be in joules, so we're going to use the 8.314 joules per mole Kelvin R value, times the temperature, which of course has to be in Kelvin, and Q is how we calculate equilibrium constant, but maybe we're not at equilibrium yet, okay? So remember, you calculate like K. Okay, so this is how we find if something is going to be thermodynamically favored or not at any given temperature, whether we're at 25 degrees Celsius or not. Now, at equilibrium, if we were at equilibrium, that would be when Q is K, right? Q is K at equilibrium. That actually means also that delta G is going to be 0. It's not favored to move one way or the other. So delta G 0 also means at equilibrium. Okay, so if we're at K, if we're at delta G equals 0, both of those things indicate equilibrium. All right, so okay, this little graph here kind of shows how these things all go together. Okay, so at equilibrium, neither the forward or the reverse reaction is spontaneous, right? If Q is K, delta G is 0, you're kind of at a standstill. Now you have forward and reverse reactions happening, they're just at the same rate, so one doesn't overpower the other. Now, if you go to the left, okay, if Q was less than K, meaning that I have more N2 and H2, so reactants in this case, if I had more reactants, then my Q value is going to get smaller, because remember, it's products of reactants. So if I have a smaller value, that means I'm on this side. And if I have more reactants than I'm supposed to, that means it's going to go in the forward reaction according to Le Chatelier's principle, and it would be spontaneous in the forward reaction. And the opposite would be true if I had too much NH3. Okay, so I'm going toward pure NH3 over here. The more NH3 I have, that would mean my Q value is big, because again, it's products over reactants. And to get to K, I'm going to have to shift to the left. So the backward reaction would be spontaneous, or we could say that the forward is not spontaneous. All right, so they're all related. Delta G, K, Q, all that jazz. So we have this equation. Now I can also then simplify that for if we are at equilibrium, right? Delta G naught equals negative R T L N K. All right, so this one is if we're not at right to that 25 degrees Celsius and 1 atmosphere. Okay, or equilibrium, or whatever you want to say. And down here, we can plug in if we actually have the K value and we're at 25 degrees Celsius and 1 atmosphere. All right, so these equations are in your equation sheet, and we are going to use them. So we've talked about 3 different ways to calculate delta G. Now we're going to implement this one. All right, so example number 8. If the delta G for a reaction is negative 25 kilojoules per mole, what is the K value? All right, now when you're approaching these problems, all you have to do is look at what you have values for and then find the equation that lends itself to what you have values for. So in this case, I have I'm going to pull it out. Delta G is negative 25 kilojoules per mole. What is the K? So I'm looking for K. So I need an equation that has delta G naught and K. Well, I have that one right here. So all I'm going to do is plug and chug and solve for K. All right, so I would do negative 25 kilojoules per mole. I am going to convert that into joules because my T value here is in joules. All right, so 1 kilojoule per 1,000 joules. So delta G naught equals RT, so negative RT. So R is 8.314 joules per mole Kelvin times T, temperature. If we're in that, remember that's 25 degrees Celsius, which is 298 K. So all of these are going to be at 298 K. So anytime you're using this is 298 K. All right, so we got 298 K. So it's G, delta G naught equals negative RT, and then the natural log of K. So I need to solve for K. All right, mathematically speaking, I'm gonna get this down to algebra. I get down to natural log of K is 10.085. To solve for K, you need to do e to the little e, to the 10.085, and then you will get that K is 23991. All right, now let's think about K values for a minute. If K is really, really big, that means that the right side or the forward reaction is favored. Favored, okay? Does this make sense with the delta G we have? Well, the delta G is negative, which means it is favored thermodynamically. So everything goes together, it all matches. The question says, does this K agree with the thermodynamic favorability of the reaction? Yes, and it should. If it doesn't, you did something wrong. All right, so I want you guys to try example 9 here. Find delta G for the reaction. Notice this does not have a little knots on it, so it's not at 25 degrees Celsius. And I gave you values so you can calculate Q. All right, so you're going to do that one and then check your answer. Okay, so I calculated Q just like K, products over reactants. This one's squared because it's got a 2. This one's cubed because it's got a 3. All right. So then I'm like, what is delta G? Well, the only equation I have that has regular delta G, not delta G naught, is this one. Okay, so use that equation, plug in all your stuff, make sure that your units match. Okay, so I did convert this one into joules, R, T, L, and Q, and got negative 42,500 joules or negative 42.5 kilojoules, which means this reaction is spontaneous. All right, example number 10, I'm not going to tell you how to do this one. Try to figure it out using the values I give you, and what equation should you use? Okay, so what I did first, I haven't even solved this yet, is I pulled out the things that I know to figure out what equation I need. Well, first of all, it says, what is the delta G naught F? So that's formation of blah. Okay. Now, if I'm working with a delta G naught F, the only equation I have that has formations in it is this one here, the sum of. Okay, so delta H naught of a reaction is equal to the sum of the delta G, or G naught of the products minus the G naught of the reactants. All right, so I know I have to use this equation. All right, I'm going to keep reading. I'm pulling stuff out. I have a K value, KSP specifically. So if it's KSP, I went ahead and wrote the equation for the KSP for this guy. For BaSO4 is 1.1 times 10 to the negative 10th. Okay, well, I have a K value. All right, now the only thing I have that relates delta G and K is this equation. So I know I'm going to need that one too. Okay, so delta G naught equals negative RTLNK. All right, I know I need that. And I'm giving you a formation for this thing and a formation for this thing. So once I write out my equation, I have the formation for this. I have the formation for this. I don't have it for this, okay? So these are related. This value and this value are the same thing, delta G naught of a reaction. So if I can solve one, I can plug it in and use it to solve the other. So the first thing I would do is plug this in, solve for delta G naught. Okay, and then for this reaction, for which I get 56.84 kilojoules. I did put it back into kilojoules because these values are in kilojoules. So that is that value. So I would then do 56.84 equals, plug in the ones that I got, products minus reactants, solve for the one that I'm missing. Okay, so I would get negative 560.7, that's one product, plus this is the one I'm looking for. I don't know that one. It's products minus reactants. The reactant is negative 1353. Okay, and you should get, once you do your algebra, that X is negative 735.5 kilojoules per mole. That would be the delta G formation of that missing ion in this equation. Okay, so the last thing I want to talk about, I'm talking about this whole temperature dependencies equations to calculate delta G. There's one more, well, really kind of two more equations that relate K, delta G, and it's really just a combination of these, kind of you integrate them together and do all your plugging and chugging, and I'm going to go hand wavy to get from this equation and this equation, which we use a lot, to, if I were to graph it, this equation here. Oh, that's not supposed to have two natural logs. Okay. The natural log of K equals negative delta H over R times 1 over T. So this incorporates everything in from these equations together. So it's if you have K and delta G and delta S and temperature and delta S, everything is together. So this is the Y equals MX plus B form. So in lab, for example, we will use these and we will actually graph it. Okay, so use this if you have graphing data. And if you have just a 2-point equation, so right as our temperature changes, our K value changes, we've done this before, but I give you delta H values. This is our 2-point equation. So if I want you to find K at a different temperature, and we have K at 1 temperature. So we have these equations, one is for graph and one is for 2-point. So how do you know when to use these? Well, if I have K and temperature with delta H, or sorry, not delta G, delta H and delta S not, okay? So if I have K, but I'm looking for temperature, or I have temperature, but I'm looking for K for that different temperature, these are the equations that you are going to have to use, one of them. You either graph it, you use the slope, or you plug it into the 2-point equation. You can do either one, though the graphing is better if you have multiple data points, okay? So example number 11, I said use delta G from example 6a. So let's pull that down. Delta G naught from example 6a was negative 24.7 kilojoules per mole. To determine the equilibrium constant is K. So I'm looking for K. Under standard conditions, so that's at 25 degrees Celsius and 1 atmosphere for this reaction. Then determine the equilibrium constant. So I want another K. That means I have 2 K values. So I'm going to have to use this 2-point equation at a different temperature. So when temperature is 450 Kelvin. All right. Well, and this one was at 25, so 298 Kelvin. Using delta S found in 5A. So delta S naught was, where is it? Negative 221.46. And I think that was, yes, joules per mole Kelvin. So I have a delta G, I have a delta S, I have K. So I want you to kind of mull with this for a little bit, pause it, and try to figure it out on your
own. Okay, Kara's going to help me walk through this one. So essentially, once I pulled all of that information down, I did 3 different steps because I really needed 3 different equations. This kind of incorporates everything that we've been doing. Well, first of all, I had to use delta G equals delta H minus T delta S because, well, I had delta S and I had delta G and I could find delta H, which I knew I was going to need because I was going to have to use the 2-point equation because I want the other K. So the only equation that has 2 K values in it is going to be this equation here. So we do have to do 2 Ks, which means I need delta H in order to do this equation. So I found delta H via that, and now I did make sure everything was in joules. This was in joules. I converted this one to joules, and I got the delta H is negative 20728 joules. Okay, well, I have delta H if I'm doing this. I also need one of the K values. So the first thing I did was find find K at 25 degrees Celsius. Okay, so I know K and delta G are related via this equation. So I did delta G, which I had, equals negative RT ln K. So I could solve for K pretty easily. Again, make sure everything's in joules. I got K is 21260 joules. This was for 298 K specifically. All right, so I have K at 298. I have delta H. Now I can use this 2-point equation. Now, you can technically do the unknown as K1 or K2. I did the one I didn't know as K2. So K2 is the one I didn't know. I'm trying to find that for, what was it, 450? Yeah, 450 Kelvin. So that was T2. K1 is the one I calculated, and T1 is 298. I wrote 0.15, but 298 is fine. I would solve the right side, I get negative 12.351. And then remember to break up a natural log. If it's divided, it would be natural log of K minus natural log of what's on the bottom. So I wrote that down here. Okay, moved this over, solved for K, e to the, and I think I couldn't quite read my answer, but it's 0.091, I think, men. But anyway, this is a K value for when I change the temperature. Now go back and make sure your answer makes sense, right? So we had a negative delta G to begin with. So this is spontaneous. Sorry. Okay, the negative delta G means it is spontaneous at normal temperature, so at 298 K. Now that also goes along with the K value that I found here, because K is, I forgot to pin this one, because K is 21260 joules, so it's positive, it's really, really big. That means it is favored in the forward direction. Delta S is negative. I get delta H is negative, so if they're both negative, it is temperature dependent. So if you noticed, as I changed the temperature, so I heated it up, K is going to change because K changes with temperature. I got 0.0919. This is less than 1. This is not favored. So as this gets hotter, it becomes less favorable, okay? Which again makes sense because my delta H is going to change it's not going to change. As my temperature changes, my delta G is going to change, and now it would be unfavorable at this new temperature. Okay, so you could go back and like calculate delta G for not at 25 degrees Celsius if you wanted to. So there's all kinds of these things that you can do. You just got to look at what you have and what equations you can use to solve for what the question is asking for. So take a minute, break it down, and that is the best advice I can give for these thermodynamics questions.